So I'm going to start by explaining a bit more what I mean by the term temporal locality. I'm then going to discuss some of the historical and social reasons why the assumption of temporal locality is so prevalent in physics. I'm then going to argue that there are various indications from modern physics that temporal locality is no longer working for us, and we should consider discarding that assumption. We'll then have a brief hiatus to ask, does any of this really matter? And I'm sure you won't be shocked to learn that I'm going to argue it does matter. I'm then going to advertise a few cool recent results on this subject from a variety of authors. And then finally, I'm going to present a result of my own about the connection between no signaling and global determinism. So first off, what is temporal locality? So as you might expect, temporal locality is closely analogous to this slide. I've basically just taken a standard definition of spatial locality from a presentation of Bell's theorem, and I've altered some of the terms to refer to temporal aspects rather than spatial aspects of the world. So what this definition essentially says is that the results of a measurement at a given time can depend only on the state of the world at that given time. And so there's a sort of a common paradigm for thinking about physics where we suppose that the universe kind of works like a computer. So it takes an initial state, it evolves that initial state forward in time via dynamical evolution. And if that's the paradigm you have in mind when you think about physics, then the assumption of temporal locality obviously seems very natural, because the whole point of this time evolution thing is that the relationships between events at different times is mediated by the information carried in the forward evolving state, and that there is no interaction between times that isn't mediated by that state. But of course, we can quite easily conceptualize ways in which the world would fail to be temporally local. So for example, the world could be temporally non-local in virtue of being governed by non-Markovian laws. So that is to say, laws where the evolution at a given time depend on states on past states as well as the present state. And there's already quite a well-established field of mathematics studying non-Markovian laws, so we do know how to handle that sort of thing mathematically. Another possibility is that the world could be temporally non-local in virtue of being retrocausal. So that would be the case if events at a given time depend on events in the future without mediation by the present state of the world. So note that we couldn't have temporal non-locality of the retrocausal kind in a world which is deterministic in the usual sense. And that's because if the world is deterministic in the sense that the future is fully defined by the present, then there aren't any facts about the future which aren't already inferred by the present. And so we could always say that dependence on the future was mediated by the present state. But of course, the indications from quantum mechanics are that the world is not deterministic in this sense, and therefore the door is still open for temporal non-locality of the retrocausal type. And then finally, the world could be temporally non-local in virtue of being governed by atemporal laws. So laws which apply to the whole of the universe all at once, in a sort of atemporal outside of history sense. And that might sound very esoteric, but we're actually very well accustomed to these sorts of laws because we apply them whenever we solve problems using an action principle or by optimizing some sort of Lagrangian over the course of history of a particle. And so we standardly tend to think of the description of the world which has states evolving forwards in time as the one that corresponds to reality, and the action principle or Lagrangian description as being in some sense just a useful calculational tool. But there's no reason we have to do that. We certainly could take the action principle description as being a description of reality. And in that case, that would certainly be a temporally non-local description because events at a given time would depend on events at various other times in a direct way without being mediated by states. So as I say, the assumption, it's very common throughout physics to assume temporal locality, to work within this picture where we suppose that the universe takes states and evolves them forward in time. And I want to explore some of the reasons why that assumption might be so prevalent. And so first of all, there's clear practical reasons, right? Science comes from an essentially pragmatic motivation where, ancient people wanted to be able to predict how their crops were going to grow, what would happen if they mix various substances. And so scientists have historically and almost universally tended to write down laws which take facts about the present and evolve them forth into the future. And it's very natural to sort of suppose that the laws that scientists write down are the laws of nature. But for those of us who are realists about the laws of nature, we should make a distinction between the true underlying laws and the laws that human scientists write down. And there's no reason why those two types of laws need to be identical. And indeed, I think it would be rather strange if the true laws of nature were designed in a way that were so convenient for us. So our pragmatic desires to write down these laws which evolve forward in time shouldn't be taken as any sort of evidence that the real laws of nature are of that form. A second consideration is the fact that we ourselves experience the present as being specially privileged, and from our first-person point of view, it seems quite clear that there's a distinction between past and present and future, and that way of thinking is codified in the philosophical view of presentism, which says that essentially the present is the only thing that's real, and that there's a process of temporal becoming where the future becomes the present. And I think very few modern physicists would self-identify as presentists, but nonetheless, there is a sense in which that particular view of the present as specially privileged has an influence on the way we think about physics, and I think makes us inclined to take this assumption of temporal locality more seriously than we perhaps have evidence for. And finally, there's a sense in which the assumption of temporal locality is kind of built into the way we're taught to do physics. And that's because basically since the time of Newton, it's been very standard to present scientific theories in terms of setting out some kinematics, that is a state space for the theory, and some dynamics, that is some laws by which the states are allowed to evolve forwards in time. And the important thing to note is that a theory set out within that classification is automatically temporally local, because the whole idea of the state of space and the evolution is that information is carried forward in time by the states and thus mediated by them. So by teaching physicists to present their theories in this form, we're kind of mandating that they should come up with temporally local theories, and we're teaching them that all acceptable scientific theories should take this form. Which means that this way of thinking kind of excludes a whole space of possible types of theories, which aren't easily or perhaps can't at all be put in this form. So there are a range of reasons why we make this assumption of temporal locality, but I think it's clear that they're sort of psychological and historical and social reasons rather than like good epistemic justifications. And indeed, I'm not really aware of anywhere where anybody takes time to justify this assumption or to explain why it's a good assumption. And I would argue that any assumption which is so widespread and yet so seldom discussed and so seldom justified is in serious danger of becoming a dogma. So I think that alone is reason enough to be quite suspicious of temporal locality. But in addition, there's some good evidence from various facets of modern physics that the assumption of temporal locality is pretty dodgy and should be looked into. So first off, if you remember, when I defined temporal locality, I said that it involves the idea that the results of measurements at a given time can depend only on the state of the world at that time. And if there are any relativists here, that might have made you a bit uncomfortable because, of course, within relativity, the state of the world at a given time isn't even well defined. What counts as the state of the world at a given time will depend on your frame of reference. And so it kind of looks like temporal locality is just straightforwardly incoherent in a relativistic context. No, that's not quite true, because in fact, you can have temporal locality in a relativistic context if you also have spatial locality, because in a theory which is both spatially and temporally local, then the results of measurements at a given time depend only on the state of the system at the space-time location of the measurement. And of course, space-time locations are well defined even within relativity. The problem comes if you want to have temporal locality and spatial non-locality, because of course an instance of spatial non-locality can be transformed into an instance of temporal non-locality just by a change of reference frame. And so it seems you're going to have trouble if you want to keep spatial non-locality, temporal locality, and special relativity all together. There's a tension between those three ideas that really is very difficult to reconcile. And so the desire to kind of keep temporal locality is what leads to comments in the interpretation of quantum mechanics about things like the wave function collapsing everywhere on a time slice, or instantaneous changes of the state of the quantum state of the world everywhere. And it's that kind of idea, that the assumption that there must be a well-defined time when the quantum state collapses, which is basically what leads to the tension with relativity. So if we want to have consistency between relativity and quantum mechanics, we really only have two options. One is to somehow get rid of spatial non-locality by adopting superdeterminism or something like that. And the other is to accept both spatial non-locality and temporal non-locality. And as I guess you can tell, I personally, my money is on the temporal non-locality option. So moving to general relativity, I think there's also good evidence coming from general relativity, particularly for the sort of atemporal all-at-once type of approach. And so that's because the solution to the Einstein equations is not a state of the world at a time. The solution to the Einstein equations is an entire course of history. So the Einstein equations in their standard presentation are exactly what I've been talking about in terms of the sort of all-at-once atemporal type of law. So that's not a conclusive argument, because the Einstein equations can be reformulated to give a more standard sort of initial value formulation where we take an initial state and evolve it forwards. But how this is done is that the Einstein equation is split into two parts. So the first set of equations become constraint equations, which govern what the allowed initial states of the universe are, and the other set of equations become the evolution equations, which evolve that state forward in time. And the point I want to make is that the point of these constraint equations is to ensure that the initial state always evolves into other allowed states. And so there's a sense in which, by imposing these constraint equations, we're actually sneaking temporal non-locality in and through the back door, because we're making the allowed initial states depend on facts about the future evolution of the initial state. So I would argue that even in this more conventional initial value formulation, the general relativity is still most sensibly interpreted as sort of all-at-once temporally non-local theory. And so given that we have at least one all-at-once temporally non-local theory, that gives us good reason to take that kind of picture seriously in other areas of physics as well. Okay, so at this point you may be thinking this is all very well, but does it really matter? And indeed, I think there are probably many physicists who would kind of accept that temporal locality is a bit dodgy, but would also say, well, it's kind of a harmless simplification, it makes it easier to do things, and ultimately we are interested in writing down theories that predict the future, so why not make this assumption? But I think this assumption is actually very far from harmless. I think it's really constraining the way in which we allow ourselves to think about physics, with pretty problematic consequences for the way that physics as a field has unfolded. And I want to explore that by considering as a case study the field of quantum foundations, which is perhaps what I personally know the best. And so the assumption of temporal locality has had a really major effect on the way that quantum foundations has developed over the last 25 years or so. So that in particular, that's because of something known as the ontological models framework. So the ontological models framework is kind of an idea that's been floating around for a while. Indeed, Bell's theorem is basically uses what we might regard as an early precursor of the ontological models framework. But this framework was made formal by Rob Speckens, who developed it who developed the sort of mathematical formalism to go along with it, and derived some very nice results with it, including several proofs regarding contextuality in quantum mechanics. And then this framework has then been used to derive pretty much every other major result in the field ever since. So the Kolbeck-Renner theorem, the PBR theorem, a great many different results in the field have all come out of this framework. And so the key point I want to make is that in the ontological models framework, basically what we do is we assume that that systems have fixed a real ontic state at a given time. The ontic state might just be the quantum state, or it might be the quantum state plus some other information, or it might contain less information than the quantum state. And the idea is that the relationships between measurement outcomes and preparations is supposed to be entirely mediated by the ontic state. So the preparations can affect the future only via the information carried forward and the ontic state. And we then use that mathematical formulation to derive various results about the structure of ontic states and try to understand how much information must be contained in the ontic states if we are going to reproduce the empirical results of quantum mechanics. So the ontological models framework is clearly assumes temporal locality, but more than that, temporal locality is kind of the whole point, because the whole point of this framework is to understand, how much information must be carried in the mediating states if we're going to make the empirical results work. So if you discard the assumption of temporal locality, all of these results mean something totally different, that you have to reconceptualize the whole field. So it's not really the case that we can just make the assumption of temporal locality for now and with the intention of discarding it in the future when our ideas are more advanced. The whole field is founded on this assumption, and if you get rid of that assumption, as the evidence suggests you should, you really need to rethink all of the results. I also want to make the point that most mainstream interpretations of quantum mechanics, so collapse models, de Broglie, Bohm, Everett, are in their usual presentations formulated in a temporally local way. And that's not to say that they couldn't be formulated in a temporally non-local way. And indeed, there's a formulation of the collapse models known as the GRW flash ontology, and which, as Jason has pointed out, the only way to make this flash ontology relativistically covariant is indeed to interpret it in a temporally non-local way. So there are options available to us, but nonetheless, it's very common to think of these interpretations in this temporally local sense. And given that, as we've seen, kind of the tension between relativity and quantum mechanics basically comes down to the tension between temporal locality and spatial non-locality, it seems likely that we're always going to have difficulties interpreting quantum mechanics if we insist on on temporal locality. And it seems to me that we might make better progress if we move to interpretations which don't build in this assumption, because there's probably quite a large space of interpretations out there that we haven't really considered because we've been very focused on this assumption of temporal locality. Okay, so I have complained that people don't take the much, but now I'm going to row back on that and say that there have been some really interesting results in recent years in contexts where people have not assumed temporal locality. So first off, we discussed non-Markovian laws, and there's a really nice result due to Montina, where he demonstrates that if you assume Markovian laws and you work within the ontological models framework, you find that the size of the ontological state space must grow exponentially over time. And Montina finds that distasteful and concludes that the only option is to discard the Markovian assumption, which of course leads to the non-Markovian temporally non-local framework that I discussed. There's also been a lot of really interesting work on retrocausality recently. So there's a result by Price and an evolution of it due to Leifer and Pusey, basically showing that if you want time symmetry within quantum mechanics, you have to allow a form of retrocausality. Now that might seem kind of obvious, because you might think that, well, obviously if things are time symmetric then and you have forward causality, you must have backwards causality. But there are perfectly coherent formulations of sort of classical mechanics, which are time symmetric, but which only incorporate one direction of causality. So what these results do is show that basically because of the discreteness of quantum mechanics, you can set up particular types of experiments where it seems that you do have to have retrocausality if you want to have perfect time symmetry. There's also several papers by Ken Wharton kind of exploring various concrete ideas for retrocausal models. Now, I want to reinforce here that there are several, there are kind of two competing visions of retrocausality that get brought up within the literature, and only one of them is temporally non-local. So we have some pictures of retrocausality where we have sort of a forward arrow of causality and a backward arrow of causality, and they kind of meet in the middle and make a decision in some way about what's going to happen in the middle. And so that's best exemplified, I think, by the two-state vector interpretation of quantum mechanics, where we have a forward evolving quantum state and a backward evolving quantum state, and measurement results are kind of determined by both quantum states at the point where they meet. And I think that vision of retrocausality is not really what I would describe as temporally non-local, because although there is influence from the future, that influence is also being mediated by a state. So there's kind of temporal locality, but in both directions. I think the problem with this kind of vision of retrocausality is that if you've got both a forwards arrow of causality and a backwards arrow of causality, there's always going to be the potential for them to come into conflict and to, prescribe measurement results which are inconsistent with one another. So in order to avoid that possibility, you have to put quite strong constraints on the allowed initial and final states of the system to ensure that your backwards and forwards arrows of causality always agree. And that starts to look quite sort of gerrymandered and contrived to many people. And I think that's possibly one of the reasons why physicists tend to have a bit of resistance to the idea of retrocausality, because it just looks a bit too convenient. But there's another way of thinking about retrocausality, which is temporally non-local, which I find much more plausible, and that's to see retrocausality as arising from within these sort of all at once atemporal theories. So if you think of the universe as being a sort of puzzle which is solved all at once, then inevitably what happens at a given time is dependent on the configuration of the universe, both in the past and the future. And because you're solving all at once in this way, the consistency conditions come in very naturally through this process of solving all at once. And that means we avoid this sort of problem of the clashing arrows of causality, and we have a much more, I think, consistent and believable picture of how this retrocausality could arise. And so my opinion is that I think the retrocausality community could do with making this distinction a lot clearer in their work, and also I obviously think that they should come out explicitly in favor of the latter view and favor the all at once temporally non-local approach. And then finally, there's some interesting work by Rishkov and collaborators who have been developing a framework for studying correlations, non-local correlations without assuming any causal order. And there's various interesting results have been derived within that framework. In particular, there's this great paper by Shrapnel and Costa where they basically extend the Robb-Spickens result on contextuality, and they show that even if you don't work within the standard ontological models framework, so even if you allow for retrocausality or for all-at-once models or for global variables of various kinds, you still inevitably have contextuality within quantum mechanics. So that's a really nice insight into what temporally non-local theories might look like. Okay, so I'm now going to present a result of my own about, again, trying to understand what sort of temporally non-local theories might look like. And so, as you may have gleaned, I'm most interested in the sort of all-at-once atemporal theories. And in that picture, we have generic non-local influences, because events at a given time can depend on events elsewhere, both in space and time, in a very generic way. And so that picture explains very naturally why in quantum mechanics we have spooky action at a distance. But it leaves us with kind of the opposite puzzle, because, if non-locality is so common and totally generic, why is it so limited? In particular, why can't we send signals faster than light, for example? That would be nice. So what I wanted to do in this project was try to explain that feature, or understand what features of the global, the all-at-once laws might lead to this no signaling principle, no signaling feature on a local level. And so specifically what I argue is that if we require that the laws of nature are deterministic on a global scale, that naturally leads to the no signaling principle on a local level. So first off, let's note that determinism is usually defined in a temporally local framework. So we assume that we say that a theory is deterministic if the future is fully determined by the state of the world on a particular time slice. But obviously in this global picture, we wouldn't want to put that sort of arbitrary temporal constraint on determinism. So I'm going to say that in this global all at once picture, we have determinism if the laws of nature prescribe a unique course of history. So nothing in the universe is inherent, intrinsically random or arbitrary. Everything is prescribed uniquely by the laws of nature, together with some set of initial / final conditions. Right. So basically, the reason that this constraint is relevant to no signaling is that if you have a process which allows you to send signals, you can use that process to create closed causal loops. So for example, you have Alice, and Alice is going to send a faster than light signal to Bob. Bob receives that Alice's message, and then puts the content of the message in another faster than light message, which he sends back to Alice, which Alice receives immediately prior to sending her own message, so she can use the content of that message in her original message. So we end up with a closed causal loop containing a message which has just come out of nowhere. It's not determined by anything anywhere else in the universe. So the intuition is that if the world is globally deterministic, you can't have any signaling processes, otherwise you would have something that was undetermined. So what I've done in this paper is just made that argument a little bit more formal, using the language of entropy and mutual information. So first off, we need to be clear about what specifically we're trying to derive from global determinism. So there are sort of several different things floating around in physics under the name of no signaling principle. There's a special relativistic principle which says no signal can be transmitted faster than light. And there's a quantum mechanical principle which says that you can't transmit information via measurements on entangled particles. And these principles are clearly related to one another, but they're not identical. So we need to kind of understand what is the key conceptual content which is shared between these principles that we're going to derive. Sorry for this terrible diagram. So basically, in order to identify this key conceptual content, I work within the Oreshkov process framework, and I make a distinction between what I call spatiotemporally symmetric and spatiotemporally asymmetric processes. So spatiotemporally symmetric processes are those such that you can interchange the spatiotemporal locations of the parts of the process without changing the correlations observed within the process. So, for example, performing measurements on entangled quantum particles is a spatiotemporally symmetric process, because if you switch the locations of the particles and perform the same measurements, you'll see exactly the same correlations. On the other hand, the seminar that I'm giving to you is a spatiotemporally asymmetric process, because you all have to be in my future light cone in order to hear the seminar. If we switched it around and you tried to listen to my seminar in my past light cone, you would have a bad time. So that's I think a fairly simple distinction, but it allows us to kind of formulate the no signaling principle in a simple and I think quite powerful way, which is simply to say that all spatiotemporally symmetric processes must be non-signaling. That's what is written on this slide. This just takes the standard cryptographic definition of no signaling and adds the requirement that it applies to all and only those processes which are spatiotemporally symmetric. So this clearly implies the quantum mechanical no signaling principle, because measurements on entangled quantum particles are, as I've said, spatiotemporally symmetric. It doesn't directly imply the special relativistic principle, but it does imply that information can't be transmitted faster than the fastest spatiotemporally asymmetric process, whatever that might be. And we are free to conjecture that in the actual world, that process is the transmission of electromagnetic radiation, i.e. light. Okay, so what we want to do then is derive from this assumption of global determinism the fact that you can't send signals using spatiotemporally symmetric processes. And so the key observation is that when you have a spatiotemporally symmetric process, you can use it to create a loop, as in this diagram, where we have the process, we model the process as a pair of boxes. One is accepting an input, which is something like a measurement direction, for example. The other is producing an output, which is something like a measurement outcome. We can then create two copies of this process, so two sets of boxes, and then we can separate the boxes and take them to different spatiotemporal locations, and compose them such that on one side we obtain the outcome from one box and use that as the input to the other box, and on the other side we obtain the outcome from the other set of boxes and use it as the input to the original pair of boxes. So we have a closed causal loop, as in the kind of Alice-Bob example. And so obviously we can do this using a spatiotemporally symmetric process, because we can always interchange the relationship between the input and output boxes. Obviously, we couldn't do this with a spatiotemporally asymmetric process, because if one part of the process must be in the future light cone of the other part, we can't just switch them around and send a message back in time. Okay, so given that we can create this kind of composition, the reasoning is as follows. If the world is indeed globally deterministic, then for any given instance of this process, the outcome must be obtained as a deterministic function of the input together with possibly some global variables, and those global variables are to be understood as whatever makes a process which to us looks probabilistic become deterministic on a global scale. And then, of course, if the world is globally deterministic, it must be the case that any composition of these processes remains deterministic under composition. So we say that in this composition depicted here, the outputs must be a deterministic function of any inputs plus the global variables. Here, because the inputs are being obtained from the outputs of the other process, there are no inputs left over. So we say the internal variables here, the O's produced by each box, must be a function entirely of the global variables that would determine the outcomes of the initial process. So what I've done on this, I won't go through the working in detail, but what I've done on this slide is I've written down those requirements in the language of entropies and mutual informations, and then I've just worked through using the chain rule and various other entropic identities to come to the final result. And so note that everything on this slide is based entirely on classical information theory, and because the inputs and outputs of the boxes, even if the contents of the boxes is quantum, the inputs and outputs are classical variables, so we can describe them using classical information theory. So there's no assumptions being made here about von Neumann entropy or any of its properties. This is all classical information theory. So working through, we come eventually to this line at the end, which says that the mutual information between the output of one box and the input of the other box must be zero, which is to say, it must be impossible to signal from one box to the other box. So to recap, we have shown that if the world is globally deterministic, then every spatiotemporally symmetric process must be non-signaling. And so that explains why, if we had a world which was generically, spatially and temporally non-local but deterministic, we would in fact expect to see no signaling. And I argue that by inference, the best explanation, this provides some evidence for the globally deterministic view, and more broadly for this atemporal all-at-once view. That's not the end of the story, though, because as you probably know, no signaling doesn't suffice to define the limits on quantum non-locality. So quantum mechanics is in fact not the most non-local non-signaling theory. There are sets of non-local boxes known as the PR boxes, which are non-signaling but which are more non-local than quantum mechanics. So you might reasonably ask, is it possible to define the stronger quantum bound, known as the Tyrellson bound, also from global determinism? And I have a very recent paper which is attempting to do just that. So I use a similar loop construction to derive Cyrelson's bound from global determinism by a very similar method, and then also use that to derive the quantum anomaly bound and make some remarks about the horizon problem. So that has just appeared on arXiv, I think, yesterday. So if you want to, if you're very keen, you can go and be probably the very first person to read it. What's the time? Yeah, I think that's about getting close to time. So I will refrain from making any jokes about temporal locality and will suggest that we move to questions.
Brilliant, thank you. That was fascinating. I suggest that we have a kind of 2 or 3 minute break. So come back at like 5:12 or so, and then I'll take questions. I'll take student questions first. So if there are students and you want to ask a question, then let me know. Okay, cool. You might have to say that you're a student in the chat or something, because I don't know who everyone is. Okay, I'll see everyone at 5:12.
The talk, very interesting. I have 2 questions. So the all-at-once models are a special type of retrocausal models, right? From what I understood. Sorry, I think that you are muted.
Yeah, so an all-at-once model would automatically be retrocausal because there would be sort of no local dependence on the whole configuration of the rest of the universe. But there could also be other types of retrocausal models that are not all at once.
Oh, okay. There are some retrocausal models that are not all at once, but all at once, all the all at once models are retrocausal in a certain sense. Okay. I was wondering another thing. This paper of Sally Shrapnel and Fabio Costa. Yeah. I read it some years ago, and I remember that this was sort of, if you think that contextuality should be a bad news for a model of retrocausality, and I thought that this kind of locally mediated retrocausal models, right? They are contextual in this sense of this paper. This is bad news for retrocausal models of this kind, right? That are supposedly nice retrocausal models, but they are. So what's your take on that paper, and also when I said what I said?
Yeah, so I really like this paper. I think it's great. I think the thing to say is that whether you're worried about this depends on your intuition for how natural contextuality is as a constraint to put on your models. So if you think that if you expect the empirical results to exactly reflect the underlying ontic states, then you'll be concerned about contextuality. But basically, if you think that there are sort of more complicated things going on underneath, and we can only access some sort of subset of the underlying reality, then you'll be less concerned about contextuality. And kind of what this paper does, and what even more than my more recent paper does, is explore the fact that there are principled reasons why, as local observers, we can't see everything that's going on, because we are limited to observing certain sorts of processes and certain sorts of local events, and we can't see the global variables. So from that point of view, it's actually it's unsurprising that the structure that we see wouldn't fully reflect the underlying ontic structure, because we're just seeing a subset of the theory. So I think in that context, it's not very surprising that you would see contextuality.
Mm-hmm. Okay, thank you.
Great, Chris Timson.
Thanks, Emily. That was a fascinating talk, really enjoyable. So I was wondering a bit if you were deploying a double standard. So you can tell me why this isn't so. So you were happy that that your result about deriving the no signaling principles was a good IBE for a temporally non-local view. Mm-hmm. But earlier I've been wondering why you weren't thinking of the success of typical temporally local theories to warrant an IBE to the view that in fact the laws truly are temporally local. So is it just that is this not a double standard because you actually just think the views of quantum theory, say, which attempts to be temporally local, are so awful that and disreputable that they really can't be considered? Because otherwise, I think, you know, it's reasonable to think that the temporal locality works really well. Doesn't that indicate, other things being equal, that the world is temporally local?
Yeah, so I think sort of part of the argument I've just given is trying to understand why, if there is very generic non-locality, we would still see laws which kind of look local and which obey, don't signal, and which you know, seem to be quite limited in their non-locality. So partly I'm sort of trying to explain why if there is this generic non-locality going on, we don't see it. I would also say I think the best explanation for the success of temporally local laws is the fact that scientists essentially only try to write down temporally local laws. So it's very uncommon to do anything else, and so, you know, we don't really have anything to compare against because everything we've tried is temporally local. So, you know, the fact that we've had success with temporally local laws doesn't imply that we wouldn't do better with temporally non-local laws.
But how badly are we doing? I mean, you mentioned earlier, I mean, this is just an example, it's interesting to reflect on. You mentioned earlier the flash ontology versions of GRW and in the relativistic context. And Dan Beddingham has worked on these in various ways, and his thought about how we should think about the wave function in quantum theory in the context of GRW collapses is precisely as a way of making the equations Markovian. But if you look at it, the facts about the wave function are fixed by kind of a thin sandwich of flashes. So in that picture, the world is a bit non-temporally local, and then the equations are very readily rendered temporally local by introducing the wave function as a summary of a thin sandwich of flashes. So that's a suggestive kind of case. And is your thought that that's the general model, that the best explanation then for the success of temporally local laws is that we're capturing somehow a little bit of manifestation of temporal non-locality, and if there were more temporal non-locality, then all hell would break loose, and well, yeah, the world would be very different from how we take it to be.
Yeah, again, that's kind of the argument here, is that in order to avoid, you know, rampant indeterminism, for example, you have to have quite strong limits on how much non-locality there can be, and so this explains why the world appears quite local to us, and why there's this sort of appearance of temporal ordering and temporal locality. But yeah, the argument is that the non-local case is generic and normal, and it's because we are observing from a particular local point of view that is constrained to obey these kinds of no signaling rules that we get an impression of locality, which is not really the way that things are underneath.
Great, thanks very much.
Thanks. Are there further questions, or are people confused about how to ask questions? You could just raise your hands physically. Guy.
Hi, thank you. It was a really interesting talk. So I'm wondering whether you thought about the limits of the underdetermination here, because it seems to me that you could always, for example, trade retrocausality and non-locality. So if I have two events here and there, space-like separation, and they're somehow connected, maybe there was something retrocausal that I didn't see that went here and then here, so it was local but retrocausal. So is there something that I could do with temporal non-locality that I wouldn't be able to do it with local retrocausality or with just standard non-locality?
Yeah, so you can, you're never going to be able to sort of test for temporal non-locality or write down predictions with temporal non-locality that could never be obtained by a temporally local theory. And that's because you can always suppose that as much information as you want is being stored in the current state of the world, or is being transmitted backwards in time by some retrocausal state. So my claim is not that allowing temporal non-locality makes possible theories which could not be obtained any other way, but rather that this is a different way of thinking about physics, which is likely to lead to different types of theories. And if the true underlying theory is indeed temporally non-local, then it's likely going to be much simpler in the end to write down a temporally non-local theory and derive a temporally local one from that, rather than trying to do something very complicated with information being transmitted backwards and forwards in time via mediating states which don't really exist. So I think that, although this doesn't allow you to make predictions which you couldn't make any other way, perhaps it will be much easier to make predictions this way.
Thanks.
Simon?
Yeah, hi, Emily. Thanks for that talk. Very interesting. But I guess this follows a bit up on Chris. We do seem to have non-temporal local methods in physics, and we use them extensively. The Feynman path integral formalism, one might think, is precisely such a framework, and is absolutely everywhere in particle physics. And even in the field of quantum foundations, the quantum hysteresis formalism is a sort of coarse-grained version of Feynman path integrals. So one would think there too, one has had quite a systematic exploration of some aspects of temporal non-locality. So is it that you've got in mind some specific version of temporal non-locality that is distinctively different from those? That's my question.
Yeah, so part of my argument is just that we should take these formulations more seriously. So my impression is that a lot of people still tend to take the sort of Newtonian picture with states being given at the initial time and being evolved forward as being a description of reality in some sense, and tend to regard the action in Lagrangian or path integral formulations as being in some sense a calculational device rather than a description of reality. And my argument is that I think by taking these more seriously and considering them as descriptions of the way things really are, that will help us both conceptually and also help us in terms of moving forward with future theories. I also think the usual action and path integral formulations are a bit temporally non-local, but not very. And I kind of want to move to a picture which is significantly more temporally non-local, and in particular which allows us to bring in global variables which are not accessible locally to determine the results of, for example, measurements that we would consider probabilistic from our local point of view. So I think the path integrals and the Lagrangian formulations are kind of a step in the right direction, but I think one could go much further in that direction.
If I could just add a little rider to that, one might think that the inability to construct a Hilbert space in certain relativistic particle physics models, and therefore the reliance only on path integral methods, one might think that that is grist to your mill, but you don't seem to. It is. Okay.
Yeah, no, I agree. Yeah.
Okay, good. Well, then that makes for an interesting topic, doesn't it? To what extent are there such relativistic theories that resist the construction of any Hilbert space theory? But yeah, I don't know the general answer to that, but right, anyway. Thank you.
Thanks. Okay, well, I'll put myself in the queue while people think of other questions. I was just wondering if you could say a little bit more about one of the reasons that you told us that we should worry that this isn't taken seriously, the temporal non-locality is, for example, violation or like the PBR theorem assuming some kind of temporal locality. And so I guess I wonder if you could say a bit more about that, and in particular, whether the easiest kind of temporal non-locality, the kind of one that gets just by combining relativity with sort of violation of Bell inequalities, is that sufficient to be allow us to get out of the PBR theorem?
Yes. So, the PBR theorem is one of the things that kind of got me started thinking in this direction, because basically what the PBR theorem says is that you can do that. They construct a situation where you can do various possible preparations of your quantum system, and then you do various possible measurements, and the conclusion is that if the ontic state doesn't contain all the same information as the quantum state, then the measurement won't always know which preparation took place, and therefore you'll have a violation of the observed results, the empirical results of quantum mechanics, which of course assumes that the measurement can only know about the preparation via the ontic state. But if the measurement is allowed to depend directly on the preparation, if there's a direct temporally non-local relationship between them, that immediately makes the PBR result redundant, because then you don't need any information to be carried in the ontic state. So the PBR theorem exists within this paradigm, which says, all the information must be mediated by a temporally local evolving ontic state. So as soon as you move away from that paradigm, you have to say something very different about the PBR result. So how the PBR result relates to spatial non-locality, I think my concern is that there's an inconsistency here, in that the PBR result and the ontological models framework in general allows that we can have kind of direct spatially non-local dependence, but it doesn't allow that we can have direct dependence between different times. It says that dependence between different times must be mediated by the ontic states, and that is just clearly inconsistent, given that relativistically spatial non-locality becomes temporal non-locality via a change in reference frame. So it seems kind of the project of the ontological models framework just seems kind of doesn't take that relativistic fact into account in an adequate way.
Thanks, that's really interesting. Well, maybe I'll come back in a bit. There's another question from Chris.
Thanks. So the answer to this can just be no, and that's fine. But I wonder whether you've had a chance, Emily, to think at all about how your constructions relate to general philosophical accounts, metaphysics of laws, and in particular, a kind of a David Lewis style Humean account of laws, where we're supposed to look at the pattern of particular facts, and then the laws are those generalizations which give the simplest and strongest version, sort of capture all those facts. And I may be wrong, but it feels as if that kind of conception of the nature of the law doesn't fit at all well within your framework.
Yes.
So is that a problem? And do you have a favored alternative view of laws that you like better?
Yes, so this is a good question, because this is what I'm working on at the moment. Basically, I'm not a huge fan of the Humean account of laws for the sort of standard reason that I don't find them adequately explanatory, and I want laws to explain things. I'm also not a fan of either the universals account or the sort of propensities account, because I think both of those are very reductionist in character. I think they assume that laws kind of are very local and govern relationships between sort of localized billiard ball-like bodies. And so basically I want an alternative realist view of laws, but I'm not super convinced by any of the existing realist views at the moment. So that is a thing I think we're in need of a realist view of laws which allows for more generic non-local laws.
Okay. Good. Well, I'll look forward to hearing how that what you come up with.
I think Aaron Sloman had his hand up. Was that?
Well, I'm not sure that my question is directly relevant to any particular thing that was said, but I wonder if you have any comments on it. I've been puzzling about life for a long time. And to take an example, if you have a fertilized egg, a bird's egg or an alligator egg, you have something that is enclosed in a shell, which seems to have some structure, but it's relatively unstructured. But at some time much later, there is, in one case, a chick that comes out with a huge amount of diversification of organization of feet and legs and body and brain and all kinds of different things working together. And in the other case, you get an alligator coming out of the egg. Are the processes that make that possible easy to fit in with the kinds of theories that the physicists have formulated, or are they just ignored? Is there a question there that needs to be answered in the context of the points you're discussing?
Yeah, I'm not a biologist, so I don't know a great deal about those processes, but I think there's definitely a relationship here to the sense in which we have an arrow of time, and
right.
you know, the fact that eggs grow into chicks and not vice versa, and so there's that fact of the asymmetry of time and the apparent direction of it is something that I think is a general problem for physics quite generally, and I am not convinced that any of the existing explanations is fully adequate. I have a vague intuition that the arguments I've given here are relevant to this, because basically this argument also suggests that you can kind of only have signaling in one direction, and that agency has to be kind of unidirectional, and from which you can derive a sort of sense of an arrow of time. But that's something for future work. Yeah,
well, often the example that's taken is something like dropping a cup and it smashes on the floor, and you get from something structured to something that's just a mess. Whereas in eggs, it's the opposite direction in a very spectacular way.
Yeah.
Thanks. Oliver's next.
Hi, thanks very much. This is a finger on your last interchange with Chris, and a really basic question. Why do you both think that the atemporal all at once sort of conception of laws is inhospitable to humanism?
Oh, I don't think it's inhospitable to humanism. I am just not a Humean for independent reasons. I find the Humean picture doesn't do the job that I'd like an account of laws of nature to do. But
right.
The atemporal, you could give a Humean account of this atemporal view, and indeed it would be quite natural, because basically you have a manifold of events that are related in various ways, and you would come up with your best systems account that would describe the relationships between them, and that the best system could well be an atemporal picture. So I think of the existing accounts of laws of nature, the Humean picture is probably the only one which would work with this atemporal type of law of nature, but also I'm not a Humean.
Okay, good. Well, that
inhospitable because if you did the best systems, it would give you back a temporally local probabilistic account, as opposed to a non-temporally local deterministic one. So you get you'd get the temporal locality with probabilities popping out, unless there's radical changes in actual physics. That was my thinking.
Yes,
okay.
I mean, I think it depends from which point of view you're trying to formulate the best system, because if you're trying to formulate the best system from the point of view of a local observer who is moving forward in time, the system you come up with is certainly going to be probabilistic and temporally local. But if you have a hypothetical observer who can see the whole universe and can see the relationships between everything, that hypothetical observer could certainly come up with a temporally non-local approach. So I mean, I don't know if that. I don't know if Hume would be comfortable with the idea of the hypothetical observer who can see the whole universe or not. But I think you certainly, from that point of view, could get a temporally non-local view popping out as your best system.
Can I add a finger to my finger then? So I mean, maybe this is wrong, but the way I think of it, the way informativeness of the laws has become to be thought about in the Humean framework, I think more following Ehrman than Lewis, is a kind of conditional given initial data and laws, I've got this very powerful machine.
Yes.
So I mean, what's the atemporal non-local counterpart of that account of informativeness? Is it just I can give you some stuff and I don't care where it is or how it's distributed in the universe, then given the laws I get all this extra information about other bits without any requirement of locality? Is that the thinking?
Yes. So kind of an account of exactly how that would work would have to wait on something like a decision about what types of initial conditions you're willing to give yourself. And so I think the view I'm inclined towards is Adrian Kent's approach, where basically you impose initial and final conditions, and that's meant to determine everything in between, and probably in a temporally non-local way. And so the idea is, the quantum variables are those things which are defined by the initial conditions and the final conditions, and the theory informs you about the events in between in a temporally non-local way, given the initial and final conditions. I mean, and obviously, if you're only interested in theories from a purely instrumental point of view, that's not going to be much help to you because you don't get to know the final conditions of the universe. But I think the thought is that by thinking about theories that are constructed in this way, that's going to give us more insight into building theories of the kind that we are practically interested in.
Thanks.
Hannah and Yami.
Yes, thanks. Thanks very much for the talk. I have two questions. The first one is really a clarificatory question. You don't allow in the global story any signals going from the future to the past. So in what sense is this different from all sorts, say, of the conservation laws? We can say the total mass of the universe, the total energy of the universe, total momentum of the universe in any future time determines the mass, energy, momentum in the past. We don't count this as problematic or in conflict in any way, adding anything to our local view. So, and similarly with the probabilistic patterns, right? We know that if we run this quantum process many times, we'll get a certain pattern. So this thing which we did now must fit the future pattern. In what sense, what you're suggesting is different from that?
Yes, so this relates basically to the question of kind of what agency is, and in the sense in which agency seems to be asymmetric. So I agree that there are certainly some kinds of inferences about the future we can make given information about the past, but they're not inferences that we can use to construct like closed causal loops of the kind that I've pointed out. We can't measure the mass of the universe and use it as an input to a box. And so that kind of thing is the kind of global variable that I refer to as being allowed to determine the outcome of the process. It's these kinds of variables which exist and are well defined, but which can't be used as inputs in this way, which are allowed to be outside this limit of non-signaling because they couldn't be used to create this failure of determinism.
Perhaps I failed to explain myself well, because you took the mass or energy from the present to the future. I'm saying you can take it the other way around as well, right? You can say the mass of the universe in the future determines its mass in the past. Similarly for momentum and everything. But so this is no news, but you are arguing for something new. I didn't get in what sense it is new. So perhaps really I didn't understand something. So that's why it's a clarification question.
What I'm arguing for is the possibility of direct influence between the past and the future without being mediated by a state. So, in the standard view, the mass in the future depends on the mass in the present because the present state evolves forward in time and the mass is preserved. So the view that I advocate would get rid of the intervening state and say that the mass in the future depends directly on the mass in the present without the need for an intervening evolving state.
Right, okay, that helps. It's a bit similar to the probabilistic pattern, right? So I'm making some experiment now, I get one result, doesn't fit any pattern, but I know that the future, it must fit into the future pattern. And this is without anything going back from the future to the past now and
Yes, indeed. And I think this kind of non-local coordination gives you a new way of thinking about objective probabilities, which makes them, I think, much easier to understand, because rather than thinking of objective probability as some sort of local intrinsic property of the system, you can think of objective probabilities as involving kind of non-local coordination across time and space between systems of various types. And I think that is a lot easier to understand than any other account of objective probability.
Okay, thanks. That helps. I have another question, but perhaps there are other questions, so I'll stop now in case.
You can say your second question.
Thanks. This is something which is kind of with overlaps tangential to what you've been doing about retrocausality. So this is a debate, in which I took part in the past, and going back to discussions in special relativity, there's this discussion about the conventionality of simultaneity, conventionality of temporal determinations, and so on. And there's a line going back at least to Reichenbach, actually even much further back to Kant, and then Poincaré and others, and arguably we find it in Einstein, saying that the only way to have a non-conventional temporal order is by connecting it to the causal order. So only the causal order determines a non-conventional temporal order. If you reject that, then in special relativity, you are left with total conventionality. If you accept it, then you have to reject backward or retrocausality, because the causal order determines temporal order. I don't know whether you are familiar with this debate, or whether you have a view on this. I'd be interested to hear if you do.
Yes, so I mean, I think that the term cause is a bit ambiguous and is used in various different ways. And there are some ways in which we use cause, in which it's associated with a particular temporal direction. And the type of causation that's going on in retrocausality and the kind of all-at-once model is, in some sense, causation in quite a loose sense. So there's relationships, there's dependence. Perhaps if you want to use causation in a specific way to be associated with time direction, you might not want to call that causality. And I myself am not particularly attached to calling it causality. I regard this type of all-at-once model as being aligned with the retrocausal view, because you do get these dependencies between results, between events now and events at some point in the future. But I don't think you need to describe that as being a causal relationship if you've got a theory of causality which doesn't allow that. You could describe it as a non-causal dependence, and that wouldn't substantially change the view.
So it's like regularities which are not mediated by a continuous process.
Yes.
That's the main thing here.
Yes, that's the idea, yeah.
Thanks again.
Brilliant. Francisco?
Yeah, so thanks for your seminar. I had two very naive questions. So one of them was, your result is using quantum measurements, but classical communication channels. So I was wondering if you have maybe thought or already made some calculations about what would happen if you used quantum communication channels and the von Neumann entropy approach that you briefly mentioned. So
the result doesn't actually use quantum measurements either. The result is passed in the language of general operational theories. So we have some black boxes which take inputs and produce outputs, and we're just trying to kind of constrain in a very general way what the relationship between those inputs and outputs could be. And so what we come out with is the fact that if the process is always deterministic, there must be no signaling. And in my more recent paper, that I do a similar thing, but I derive a more specific limit, which is the specific quantum limit out the Tyrellson bound, and that's done basically going via information causality, which is an information theoretic principle that's known to produce a Tyrellson bound. So I wanted to avoid using quantum principles or quantum von Neumann entropies, because I kind of am trying to explain why quantum mechanics is the way it is. So I'm not wanting to presuppose any quantum principles.
Okay, thanks. I understand. And my second question, I kept thinking about what Professor Saunders was saying about particle physics, and the other naive example of temporal locality that I thought is, so in particle physics and in quantum field theory in general, pretty much everything we can measure is based on scattering results. Yeah. And in scattering results, unless we are only dealing with asymptotically past or asymptotically future states, you really have to worry about the precise nature of the interaction, which is, as far as I understand, quite temporally and spatially localized, and otherwise it is not well formulated. So yes. Where would you stand on those sort of ideas?
Yes, so again, the things that we can measure in scattering experiments are governed by the same kind of rules that I considered here in this very simple toy model. And so the idea is that any types of variables that we can access and measure locally must obey signaling, and they must obey various other constraints that arise from this determinism requirement. And so that is meant to explain why we get why it seems to us that we can mostly assume locality and consider only local interactions, because because the requirement of determinism basically implies that you can't have too much non-locality. And so I haven't considered the particle physics case in detail, but I think the same argument would apply here, that you would get an appearance of locality because determinism would prevent you from having too much non-locality in that case.
Great, thanks.
Oliver?
So this is a bit of a left field question, I think. And it may be difficult to answer if these global all at once laws are just the framework where you want physics to go, rather than you're having a sort of very firm idea of what they might look like. But I mean, one thing that's occurring to me is that the distinction between time and space seems to be very bound up with notions of causation and local aspects of the universe. Mm-hmm. So I'm wondering whether the way you're thinking about the global still has a role for that distinction. So the way you've been discussing things, you're using spatiotemporal talk all the time, but yeah. I'm wondering whether that really survives or is going to survive in the ultimate picture.
Yeah, so
or whether it's going to be an emergent thing.
Yeah, sorry. I think absolutely it would be emergent. So I don't have obviously don't have a concrete model, but kind of the vision I have in mind is that we have a sort of manifold of point-like events which are related to one another in various ways, and by imposing constraints like the one I've just discussed, we would get constraints on the ways in which they're allowed to be related to each other, and basically that in order to prevent loops and various other problematic configurations, you would get a kind of space-time that would be built up out of that, and it would kind of have to be directed and have limits on the ways in which processes can be related to maintain that determinism. So definitely, I think space-time I would want to be emergent out of the relationships between events rather than being predefined.
Brilliant. Are there any further questions? Hannah, you can go again.
Thanks again. If there aren't any, I see that Francisco. Oh no, that's the one who just asked. I've been thinking a bit on your response, and you know, this non-continuous correlations between future and past. Is it immune to bulking arguments? So, you know, we scientists, we work out the regularities. We say, all right, this is now going on like this because in the future, so let's stop it from happening. And we do whatever to stop it from happening. You should stop such bulking somehow. How do you do that?
Well, I think the bilking problem is related to the closed causal loop problem. And so my argument, which rules out closed causal loops, I think would also rule out bilking for the same sorts of reasons, that if we had that sort of influence, if we had sufficient agency in both directions, that would lead to indeterminism, which by this argument is not allowed.
So it's a kind of a correlation with something in the future, which cannot be determined. You know, we cannot determine in the present anything about the future, and
yeah. So
can we try to you know at random change things or make the future different in all sorts of ways to stop such regularities?
I mean, clearly we can change the future. I think the issue is that our knowledge of the future is limited in certain specific ways, and it's limited partly by the fact that the ways in which the future can influence the present has to be limited in such a way that closed causal loops don't arise, and that constraint rules out the possibility of preventing the future from happening, basically. Because the model is solved all at once, the all at once solving will naturally impose consistency conditions on everything that happens, and you, from inside the universe, from inside the solution, you can't alter that solution.
It's not exactly causal loops. It's like, you know, I observe what has happened up till now, and I see that events at time t are correlated with the events at time t plus 10. Mm-hmm. This has been the cause so far. I don't see any influence between t plus 10 to t. And I say, well, let's now try to destroy this regularity. Now at t, I know what should be at t plus 10 in order to have this regularity. I'll stop it from happening. So it's not signals, it's a kind of the ability even to discover the regularity.
Yes, but I mean, in this all at once picture, we, the scientists, and all our thoughts and decisions are part of the all at once model, which is solved atemporally from outside, and therefore, you know, we as people located within the universe can't possibly alter that solution because it's determined outside of the universe. So whatever thought process you might have and whatever discoveries we can make necessarily have to obey these consistency conditions which are imposed externally.
Yes, perhaps at the end of the day, it comes back to the point Aaron Sloman made. There are issues coming from biology, from human deliberation, and it's a question, how can they fit into this physics picture?
Yeah. Guy, that's really maybe the last question.
Thanks. So just two close questions, so ask them together. One, you mentioned fine-tuning. So if, we would be glad if you could say a bit more about this, how it fits in. And the second question is whether you thought about superdeterminism.
So fine-tuning, yeah. So I didn't talk about this, but the reason I mentioned fine-tuning is that there's this nice argument due to Rob Speckens and some other people, which shows that in order to produce correlations which are non-local but non-signaling, to produce that with a sort of underlying causal model in the Judeo-Pearl tradition, you have to have a fine-tuned causal model. You can't. There's no natural way to achieve that, and so that was meant to be motivation for this question of why do we have non-signaling in a non-local model? It seems quite unreasonable and conspiratorial if you look at it from this point of view. So it's this kind of fine-tuned causal influence that seems to be, to me, in need of explanation. So that was meant to be motivation for why I wanted to give an explanation of that. Sorry, what was the second question?
Thanks. About superdeterminism, if you talk about this, if it's related to.
Yes, superdeterminism. Yeah, basically, as I say, I think the options for interpreting quantum mechanics come down to either getting rid of spatial non-locality, and the best way I know of doing that is via superdeterminism. So allowing that in a Bell experiment, our measurement choices can depend on the underlying ontic state in some sense, so getting rid of free will. Or if you don't want to do that, which a lot of people don't want to do that, the only other realistic alternative is to accept temporal non-locality.
Thanks.
All right, brilliant. I think we should end there, but that was really, really fascinating. Thank you so much. And
very much.
Unmute and clap. But also, just before that, next term the next meeting will have Katie Robertson. So keep an eye on the website if anyone wants to join for that. Okay, awesome. All right.
Great, thank you.